Hi, anyone there? Can you guys hear me? Lokesh, can you hear me? Let me uh, go over. Let's wait for 2 3 minutes. Until then, I'll just see what the problem is. I will try to go over the same problem that I have went yesterday because I haven't tried it yet. Not I haven't tried it. Little bit. I won't do that the whole stream. Okay. See the yesterday's problem. Oh, we have 6 viewers already. I'll try for 10 viewers. Okay. Is it modulo G? 1 minute. So wait a minute, because someone has asked me, I'll try this, but then I won't try yesterday's problem for long time. Okay, I will only try it for some time. Okay, I will only try it for some time, and then we can try some other problem. Okay, we have 10 viewers. So what I will do is I will try to solve one or two problems from that were requested here. Okay. Other than that, for 10 or 15 minutes, I will try to go over yesterday's problem. I haven't thought about it much, but then if you see this, that makes some. Fuck, why the fuck is my feel like this? Yeah. So if you see this, here I'm. See, guys, really what happened yesterday was. Really what happened. Like the video. Really what happened yesterday was I got stuck thinking that we found something when we haven't found anything. Bro, you have asked me that. I don't have any time like that. I just want to solve some problem. That's it. Okay. And we have to analyze why we are taking so long. Okay. We have to analyze, like we have to analyze why yesterday took so long on some problem. I know it's a difficult problem, but once we solve it, then we have to analyze. Once you solve the problem, you have to analyze. We haven't solved the problem yet, but suppose we solve the problem, we have to analyze. I will not go too much over the problem that I tried yesterday, but let's see. uh, I will try to read this one too. uh, okay, let me see this one. So here I made it. See, mainly what happened was I got stuck thinking that we found a nice thing in the question, because when we find a nice thing in the question, like that's the right direction, but then I that was a mistake that I found a nice thing, so it got diverted because of that. Otherwise we could have stopped there. See, we have to learn when to stop. Okay, yesterday if I have been more careful, I would have known to stop here, and then I would have looked for something else, right? So what can we always do? uh, Look at optimal structure. This we can always do, right? Like the final structure. So yesterday if you see, we can say a few things. Just after contest, before sleep I just wrote something. I think one thing we can say is, uh, let's say optimal looks like 0 0 1 up to 1 x minus 1, and then we have a big jump which is difference is greater than 1. Now what can we do? If we have something like that, what can we do is, see, max plus 1, if this is the final value, right? That means it has become 0, and then it increased 1 by 1 to max plus 1. It has become 0, and then it increased 1 by 1 to max plus 1. So when it became 0, if you have delayed that, when it fallen, it will become 0, right? If you delay that, what will happen? If you delay when it became 0, what will happen? Instead of increasing max plus 1 times, it will increase only max times now, because let's say it increase it to max plus 1 times when things are falling on that, right? We can just delay when it fallen to make it max plus max. So this says something about the optimal structure, that we have an optimal value. So optimal cannot have something like this. Optimal must go till the end. We can say that about the optimal value, that 0 1, because we are, if this is the case, we can make a higher max. Let's say this is the max, we can make a higher max. So that means it goes till the end. So we only have 0 0 0 1 1 1 1 2 2 2 2 3 3 3 3 up to so on, max minus 1, max minus 1, max minus 1, max minus 1. This is the structure. We can say this thing. Is it clear till here? Hi, is that thing clear? uh, Let me be clear, because x cali draw. So what I'm saying is, we can say this about the optimal. If it is 0 0 up to so on, I think it's better here. So if it is 0 0 up to so on, max minus 1, comma max plus 1, let's say. So let's say it has this, and then we have some other elements. For this, the answer is max, right? Let's say if the optimal is like this, what can we do is this thing became 0 at some point, and then it has gotten 1 2 3 up to so on max plus 1, right? So when it became 0, if you have just delayed that one process by 2, by 1, then that would have been max, and then we have a higher max. So what can we say? Hence, in optimal we have 0 0 0 up to so on. Last element will be max minus 1. We can eliminate plus 2. Is this fine in the optimal? Hope this is fine, right? That's just some logic we can use. And then, see, I won't try this for long. Okay, I won't try this for long. That seems fine, right? And now, if we try to apply same logic again, uh, let's say we have 0 0 0 1 1 2 2 up to so on, right? Can I make, can I reduce something? Can I reduce this 2 to 1? Can I do that? If you try to see that, because here we are able to reduce max plus 1 to max, right? Can I reduce 2 to 1 without affecting other things much? If you try to see that, this has become 0 at some time, and then it increased slowly to 2, right? So if I delay that process, what happens if you delay something? If you delay a fall, what happens? So 2 has fallen, it became 0, and then it increased twice. So if I just delay that fall, it will become 1. But when it has fallen, it will fall with a bigger value. This is good for us. This is greedy. This is good, right? So when it is falling, falling with, if you delay that, what happens? Let's try to understand the logic here. So let's say that its value is 3. Okay, its value is 3. Fallen, it becomes 0. And then, so let's say uh, fallen, and then so what happened here? AI plus 1, AI plus 2, AI plus 3 became plus plus because 3 was the fallen thing. Now it something fallen on this, it became 1. Something fallen on this, it became 2. So if I delay this fallen process to here, if I delay this fallen process to here, what happens? Sorry, I'll write it down. This is one case, let's say. If I delay this fallen process, then what happens? We will have that one here. So that makes it 4. And then this will become 1. So now what happened? Also AI plus 4 will become plus plus. So this is really good, right? If you delay that, what happens? It only increases. It only becomes bigger thing. And bigger thing seems good, right? Bigger thing falling from there seems good. So delaying that seems fine. This means what? We can always delay this one, it becomes 0, it becomes 0. And then you can keep this one. You can make this 2 as 1 comma 2. You can make this 3 as 2 comma 2 comma 3 up to so on. So what can we do? We can make everything as 0. We can only keep 1 2, we can only keep 1 1, we can only keep 1 2, we can only keep 1 3, we can only keep 1 4 up to so on, max minus 1. So we can make the optimal, which is like this, into this. Like if this optimal existed, this will also exist, because we can remove this by adding more things to this, right? So let's try to see if that's true or not. Okay, so you can remove this by adding more things to that, and then what happens? This seems like it's becoming bigger, but then you can always delay and make it smaller. You can always delay and make it smaller. So its potential value is increasing, but then it will only increase by 111, right? So you will delay, and then you can control the value. So if you delay this and if you reduce that, its effect would have been higher. But again, you can delay, because if some more things are, whatever has fallen, it affects more things now. But you can always delay things. You can always delay when this has fallen, right? If it is falling before, it doesn't matter. If it is falling after, we have to be careful about that too, because we have to be careful about this statement too, because we have to use much more logic maybe. So let's not waste too much time. Let's go to some other problem. Okay, let's go to some other problem. Let's not time waste. We can come to this maybe within this week. We'll solve this problem. Okay, let's not stress too much. It's 11 minutes, because I just realized I have to apply more logic to verify this claim, because I have to apply a bit more logic to verify this claim, if this claim is true or not. Because what is my claim? uh, this becomes 0. If you delay, it will fall a bigger value. But then once you delay, what may happen? This might have already fallen. This might have already fallen. This might have already fallen. So now it's getting increased again. If it hasn't fallen, it doesn't affect the final value at all. If it has fallen, then it's making it even bigger. So you can again delay the fall, and you can make it lesser value. So that's this is holding true. If I verify carefully, this is still holding true. So let's just see, keep everything else same. Let's try to just delay when this has fallen. Okay. After this has fallen, what have happened? It increased by 1. So now we are delaying that. So now what happens, that 1 will have been fallen now first. And then let's say initially it was x, it would have been x plus 1, and then it falls. So this is 0, but it fallen a bit later. So now let's take some j here. Because of this, if it has already fallen, its value will increase. If it has not yet fallen, it will not have any effect, because finally, if you see the same operations, it's anyway going to fall. So the influence of this will be gone. So what we are doing is not complex thing. We are trying to see what happens. Let's say all the operations procedure has been there. Okay. In all the operations procedure, what we are just doing is trying to delay its fall by one more step. Then what happens, we are trying to see. And then what happens is, instead of x falling, now x plus 1 will fall. When x plus 1 will fall for some j, which is nothing but x plus 1 j, what happens is, before it was not increasing plus 1, now it will get plus 1 value. So it would have been, here it would have increased something, not decreased. If you make this 1 as 0, it will increase something over here. But increase is fine, I think, because if the final value is increased, we can still lower the value. We can still lower the value using our same logic. Now we will come here. Now we will lower that value, still maintaining everything greater than or equals to these things. And if you can maintain everything greater than or equals to these things, you can come from here to here. That's a logical thing we have to work, and then we have to come to a conclusion. I thought this needs more work, but then I was able to do very clearly that once x plus 1 falls, instead of x falling, it may influence some j which is not increasing before, but now it's increasing. So it might have become a higher value. The only result would be we have the same thing, but something might become higher. So 1 reduced to 0, everything else is same, but one thing may be becoming a bit higher. So that's the only result of this making 0. What we are doing, keeping all the operations same, just delaying when it is falling by 1. So it has increased, and x plus 1, now x plus 1 has fallen, and x plus 1 has fallen. It might have, everything else might have remained same, or one thing might be increased. But increase is fine for us because we reduce one. Okay, we have these lost these things, right? All other than that, everything we will keep reducing. Okay, everything will keep reducing. All of this will make 0, this we will make 1, this we will keep it 2. At all these processes, the next things are just increasing. And then when we come to that, we will have that, we can reduce things again and so on, and then we can come here. Do you guys see how we are using logic to prove some claim? Now I can be sure that there is an optimal array of this form, an optimal final array of this form. And this seems like a good observation for us now, right? This is what I thought after sleeping. I woke up at some time, I guess. It's the same logic. The observation was max plus 1 can be reduced without affecting others by delaying its fall. And then the observation was, after I woke up, I thought, by delaying when one thing fall, we can only make it bigger before fall, and that seems good to do. So we can always, if that makes the next things bigger, we can again go here, and then we can delay this fall. We can just change those operations to attain something bigger here, and attaining something bigger, we can come from here to here. So this seems like a good observation, right? Sorry if this is being too much logic, but try to push yourself, try to think a bit more, try to see how I am trying to use logic to make some claims, because you can see now what type of guesses you can make. Unless we prove, we cannot make this guess, right? Because even now I was confused, maybe this is wrong, I thought for a moment, and then I was trying to prove it very clearly. And how did I prove it very clearly? Kept all the operations same, only this fall has been delayed. And then when this has fallen, x plus, instead of x plus 1 would have fallen, and that would have influenced some other j by, it would have increased it. If it has not yet fallen, it will increase its value by 1, and then that falls. That will recursively handle. And if something big falls onto outside, it goes out. So it's recursively working. And if you see this value, how it will affect, once it increased, if it has not yet fallen, it will have no effect. If it has fallen, so x plus 1, right? X will influence till here, x plus 1 will influence the one more element. Now, so I'm just looking at that one more element. If it has increased, if it has already fallen, it will increase by plus 1. So we will only increase some value. Even that is fine for us. Because if you are only increasing, you can make this 1 as 0, and you can still find 1, 2, 3 up to so on, x minus 1 in the last max elements. So this says, using logic, this says that we have such an optimal structure. So if an optimal exists, it will exist like this, the first step. And then if an optimal exists, it exists like this. Using the same logic from here to here, what I have used. But what I am trying to say you people is, at difficult ratings, you cannot make guesses. If it is a smaller rating, maybe guessing such a optimal exists and then proceeding further may help you solve the problem. But even after this guess, you need much more logic to proceed further, let's say. Not much more, you need some more work to proceed further, let's say. Then you cannot verify such a guess, right? You have to prove things clearly, then you can go further. So try to understand how very difficult problems look like. 23, 22 also would not be this difficult, I guess, but I'm trying to show you like how to proceed. Because now if I have proven this very clearly, then I can say, okay, now this is true, we can proceed further, right? Does that make any sense, people? Did that make any sense? So can you guys tell me like if that made any sense to you people? I mean, this is a much more difficult problem, but you can try to see how we are applying logic, right? Trying to see the optimal, what can we say on that? Trying after, not lengthy proving too, but must be proved. If you cannot prove, you cannot go further. You must prove that, because these proofs are not too difficult to see. If you can feel that, Okay, it's increasing because yesterday I just felt that, right? And then I'm trying to prove it a bit clearly. Sometimes it won't be too simple to. So, but now what can we say? Now we can binary search too, probably. Now we can, because if this can be formed, also we can lower things, right? This can be formed, probably. So we can binary search too, and then we can solve this problem. Can you make the false to make things like this? So yesterday night, just before the stream, what I have done, I have uh, someone has told this thing. We can, no, not exact this, but someone has told we can reduce things, or we can go greedy. Something someone has told. I don't remember it much, but then, is this clear till here? I mean, you can see this is a much difficult problem, right? You guys know this is like a bit greater than 2400, I guess. So they may demand proofs. This is much difficult. Even at 22 level, it won't be needed. Okay. Even at 22 level, some guess my work, something like that may work. But if this is true, let's assume that this is true because I think the proof I have done is good enough, right? The proof I have done is good enough. So I don't want to waste time. See, yesterday, really what happened was I thought the operation is having something like this. So I went in that direction. But if we have not gone in that direction, looking at optimal and trying to comment something is basic, right? We have to always look at the optimal structure and then try to see if we can simplify it a little bit, or try to say what we can say on the optimal structure. Try to say what you can say on the optimal structure. That's what we do. It's not random. Again, this is like one of the most basic idea, right? So now we can think. So now we can think. So now, see, I haven't thought of the problem before. These are the two things I got in, and then I went to work today. I did some work, I guess, in my office, and then I came back. At night, I'm trying to stream again. So now our goal is, if you are doing binary search, our goal is trying to make array A to this, right? We want to make array A to this. Can we do that in a greedy way? Is what we are trying to try now. Okay. So this should become 1. Means can we do something like fall all of this, make them make fall, make all of this fall, make all of these things fall, okay? And then you will have the maximum possible value here, right? Let's say we are making fall all of these things from this direction, okay? So once this has fallen, now I'm trying to see if there is a greedy way where we can try to. So if this is 1, what does that mean? After it has fallen, we need one operation on top of that, right? We need only one thing on top of that. We need one thing falling on that. So, but this seems somehow doable. If you can answer this question, can you try making array A into this exact array or not? You can solve the problem in login. So now it became more simpler, right? Can you make the array A to this is the question, right? So let's look at this one, okay? What does it say? Can you increase this to this much while making all of these things this? I'm not able to think. I may need some time to think too, but See, let's keep it till here. Let's keep it till here. I will come back to this problem. We don't wanna drift away. Okay, I can think on this too because I think now it doesn't seem that difficult. We have to find a greedy way. We have to find a greedy way, right? So if this is becoming one, if this is becoming one, uh, what does that mean? Something's for at least one thing should fall on this, right? At least one thing should fall on this. At least two things should fall on this. At least three things should fall on this. At least four things should fall on this, up to so on, right? Before it falls. Sorry, after it falls at least uh, after it falls at least one thing should fall on it. After it falls at least two things should fall on this. After it falls at least three things should fall on this. After it falls at least four things should fall on it. And after this falls at least x minus one thing should fall on that. That's the constraint we have now. So let's try to keep this thing. Let's say all of these are falling. All of these are falling. Now this one element has not yet fallen, but then it will have some very big value, right? If you come from this side, that's the most greedy thing we can do. And then it will have, let's say we are assuming that all of these are falling onto forward. All of these are falling forward. And then because coming from this side is the best greedily, because once that came here, now both of them will go further, right? That's the most greedy thing we can do coming from this side. Coming from this side is the most greedy thing we can do to collect all these things. So now we're trying to collect all these things, and then all of them has fallen here, which makes one value, whatever its initial value is. Let's say x is its initial value. Let's say x is its initial value. It might have become x plus some z, x plus 1, x plus 2, up to so on x plus z. Okay, now what we will do, we want this to have, now if you apply, now if you make this fall, it will become 0, but then what we want it to be, we want it to be 1. So what do? We have to, we have to before the last thing falling on that, we have to make it fall. So now what will happen, all of these things would have been executed, but then when this thing is falling, we will have this falling just before that. So we have this falling just before that, and it must, it must be, see, all these things have fallen, and now this is falling. Only one can be, can fall after this, and one must fall after that on this, right? Only one can fall after that, and one must fall after that. So we're trying to take the maximum one to fall after this. So all this will fall, and then now this will fall, and then this will fall. Maybe that's the most greedy thing you can do. And now what we will do? Now these things have been ordered, right? The ordering of these things have been done. Now for this two, we have to take the biggest. We have to take the biggest two things here, because see, one must go before two things that will come till here. Okay, one must go before two things that will come till here, and then two must go before two things that will come till here. That's the restriction. And then three must go before the two things that will come till here. Maybe some greedy works, or maybe some greedy doesn't work, but So now probably some greedy works here, some greedy way to make the array A into this one, to verify that if we can make in a greedy way from the array A to this or not. Yeah, because we can use binary search. Then yeah, let me stop here. Okay, let me stop here, and then I will try to solve some other problem that some of you asks me. Okay, and then I'll try to come back here. So someone has asked me 2 and 2c, right? So let's try to just do one easy problem and then come back. Okay, till here it made some sense. Maybe I will save it here and then I will try to do it later. Okay, maybe there is a greedy way to verify if you can make that to this, because let's say till here we have some ordering of false. Now 2 should go at least 2 times before on things that can fall till here. That seems greedy, right? Somehow we have an ordering. Now few things can fall till 2, and now 2 should go before those things, and then it should fall then, because now two things will fall on that, and then its value will become 2. Maybe that greedy would work, but we have to prove it clearly too before trying. Okay, do you guys get what I mean? I know it's more logic, but still I'm giving you guys an opportunity to think more, to follow someone trying to explain a bit more thing. So see what 2 means. After 2 has fallen, after this element has fallen, two things have touched that. So what we will do is we will find an optimal greedy best way till here. Somehow that sequence is the best, let's say. Now 2 must go and find a place. 2 must go to a place where before two things falling on that. Let's say in this ordering itself, it will go to the first two things falling on that, and then it will go till there. Okay, because it must be at least, maybe that would work. Should I try to brute force that and see if that will work or not? Like O of n squared solution. It's time waste, maybe. Do you guys get have a sequence of operations still here? And then what I'm telling is move when this should fall, you have to move before one thing that's falling that. And then when this should fall, I will move it before two things that falls before that. And when this should fall, I will fall it, make it to just move in that sequence, same sequence, I'll try to move it a bit forward so that three things will fall after it falls. And then for something, if you cannot find if you cannot find four things that fall on that, then it's not possible. Then the greedy doesn't work. Then this max is not, we cannot make this max. So for 4, let's say we were not able to find four after our greedy best thing. I don't know if it is greedy best. If it is, then it is. But after our best sequence we have done, suppose there existed a best sequence, there are no four things at all that falls on this, so that we can move earlier. Then the answer is we will just return false. This is one thing. We can verify this solution in O of n square, or we can try to prove it clearly. And then if it is really true, we can probably simplify it to O of n2, because the problem can be solved in O of n, right? If it is true, we can do the same thing by simplifying it little bit. Yeah, but to not waste time, I will not much experiment here. We will go and solve some other problem and then come to this, because yesterday I wasted a lot of time, right? So I don't want to waste time. I want to create good content and then one day charge for it. I'm just joking. Uh, so we have people still. We have only 7 people, but yeah, it's fine. After 3 fall of 3, then 1 and 2 will fall. If that's so, see, what I mean is, Yash Mahota, if you move 3 to here, we cannot guarantee that if these two things will fall on 3. Maybe these two things will not fall. Maybe this one will fall on 3 and then this one will fall on 3. Then we have to move 3 before those two things. So that's a greedy way. That's a greedy way. Like, that's a greedy way, is what I mean. Okay. We have few things falling on we have few things falling on here, right? So Yash Mohata, do you get that? After three has, so what I'm telling is, let's have a sequence of false, and then when one comes, uh, among this greedy best sequence, let's say this is the only thing that falls still here. This is the only thing that falls still here. Let's say that won't happen, because if that is falling till here, also all of these will fall, right? And also, will that hold true for everything? Will that statement hold true for everything? Is that what Eshmohata is trying to say me? So, if there are two things here in that sequence that fall still here, that means, I mean, we cannot say, because one might have moved here, right? If there are two things here that fall still here, we have to move two before those two things, so that after two has fallen, those things will fall till here, okay? So we don't know. Maybe only these two things will reach till here. I was trying to say, see if last two things will always be the optimal things that fall on this, but then it doesn't seem so. So that can be one algorithm. Like we have one sequence, what's the last thing that falls on this? We'll move there. And then in that sequence, we may have just two things falling on here and here. I'm trying to think a little bit. Yeah. So at least it seems we have solved something, right? Because we came to here. From now, this is really true, because I have verified this proof a bit more clearly, I think. So here itself says this is the only direction you can go now. Probably, right? So the problem is almost solved here. Do you see? Like after getting this, we know for sure that this is right. Okay. So let's solve some easy problem and then come back here, because okay, it's 38 minutes now. So let's stop here. See, but Yashmota, do you see like this can be a very correct solution? And what's the topic we are using here? Trying to see the optimal. Is that the topic? Hi Ashmota, can we try to follow forward? Like let me like okay, is is this guy existing? Like Chaitanya Nanadikar, are you there? So I will try to read this problem. Okay, I'll try to read this problem. It seems an easy problem, right? So let's try to solve the problem using the same techniques. Okay. So see here, what we thought yesterday was simple was not simple. So we should not have gone that direction at all. If you have been careful, it's not simple. After an operation, just two things are falling, but then it also depends on when these two things will leave, right? So it's not that simple. I thought it's a simple thing, and then I went in the direction. It seems wrong if you have noticed that one of those things will leave at different times, right? Then the false will actually matter. So we could have just seen the optimal and try to make some claims. Okay, I will try it tomorrow maybe. Okay, or I will try to come back. But now this seems very right, right? This seems very right. So we have to learn why something has went wrong. Okay, that seems fine. So now let me try to do this problem. We have people. Suvam Chatre, can you listen to this problem? Like, can we try to solve this problem C, which is probably an easy problem? Alice and Bob are playing a game using an array of size n. Initially, all elements of the array are colorless. First, Alice chooses three elements and colors them red. Then Bob chooses any element and colors it blue. If it was red, recolor it. So Alice chooses three elements and colors them red. Bob chooses an element and colors it blue. Alice wins if the sum of the red elements is strictly greater than the value of the blue element. So it's not like a repeating thing. It's just that Alice will choose three things, color them red, and then Bob will just choose one element and then color it blue. Alice wins if the sum of the red elements is strictly greater than the value of the blue element. If there are only three elements, it seems very restrictive, right? Alice will must choose all of them on red, and then Bob, what will he remove? He will remove, and then we want number of ways. And then we want answer. You have to calculate the number of ways that Alice can choose three elements in order to win, regardless of Bob's actions. This is what we want. This is what we want, right? So the problem seems direct, a bit direct. So not too direct. Chaitanya Nanadika, what have you done in this problem? So one thing is very clear, right? First, find when will Alex win. Alex or Alex? Hey, when will Alex win? First, we have to regardless of Bob's choices. Is the first question, and then count it. Okay, first we have to solve this thing. Have you solved this problem, Chaitanya? Bro, you need not point what the things I'm doing wrong, okay? If I'm not doing topic streams or if I'm not letting others think, I'm giving time. Be patient, Subham, Chatre. Try to, I mean, this is the first step anyone must do, right? I'm just reading the problem and then writing this. I haven't said anything till now, okay? When will Alice win regardless of Bob's choices? We have to count these things. So I'm telling, first we have to see what is that? What is that? Yeah, so let's try to see that. Let's say we choose X, Y, Z, right? Bob can choose max among X, Y, Z, or Bob can choose max among remaining things, right? These are two things Bob can do, and whatever he do, Alice must win. It seems you're absolutely right. Is Akil Raidu, are you my friend Akil Raidu, or you are like some new Akil Raidu? Because too many people same names, right? I don't think you are my friend Akil Raidu, but yeah. So okay, nice to see you here. I need support. Yeah. So till here it seems direct. So now we have to see Bob can choose outside or Bob can choose, if he chooses the outside colorless thing, he will choose the max. If he is choosing among these things, he will choose, let's say, x less than or equals to y less than or equals to z without loss of generality, maybe. So now let's try to see in these two cases itself. I'm not even thinking. In this case, if x plus y greater than z, Alice wins. Right. So for Alice to win, what must happen? X plus y should be greater than z. That must happen. We even have this less than or equals to things, okay? What must happen? Those things doesn't matter, I know. Uh, this must happen. Otherwise, Bob would just choose Z, and then the things that allies has would not be strictly greater than this. So this should happen. And what should happen? X plus y plus z should be greater than max element. Also, this should happen, right? So these are like necessary conditions. Whenever you solve a problem, try to know exactly what you're doing. If x comma y comma z makes allies win, implies x plus y greater than z, implies x plus y plus z greater than. Okay, these are the, if x comma y comma z is a good one, then these things will happen. Now we have to see, if these things happen, is that a good pair? And then these conditions will be necessary and sufficient. Do you guys see how clearly we have to solve the problem? If that thing happens, then this is true. I know I'm complicating an easy problem too, but so now if these two things happen, x plus y plus z greater than z, then whatever he choose, we have the other two things greater than, allies strictly winning, right? Even if we choose x, we have already z greater, z plus y, both being non-zero, if there are three zeros, then this will fail, I know. Both being non-zero, if he chooses x or y, all of them being non-zero, if he chooses one of this, even then allies will win. Even if he chooses the biggest value, even then allies will win, right? Because choosing the bigger is the best, right? Even then he's failing. And also this happens, let's say, even now allies will win. So these are necessary and sufficient conditions. Most of the time we don't care after getting necessary conditions. Maybe you guys don't care if they are sufficient or not, but we can just verify once if these two are necessary and sufficient conditions or not. I mean, this problem is obvious that these two are the necessary and sufficient ones, but I'm just making like we have to be a bit clear at what we do. So now, uh, let's simplify this thing. We have max element among remaining, right? Instead of that, let's look at max element, which is uh, equals to an. Let's look at an. If m is among x comma y comma z, if m is among x comma y comma z, then are these values small? See, we have few other things. We have n being small, and we have n being small, and we have also the values being less than or equals to 10 power 5. Right. So if m is among this, then this thing automatically happens. Else x plus y plus z should be greater than or equals to m. So we can replace this with m, because if m is among this automatically happens. If m is not among these things, then also this should happen. So maximum among other things can be replaced with just maximum. So now these are the two conditions we have: x plus y being greater than z, and x plus y plus z being greater than m. Okay. So if I fix z, okay, if I fix z, then what do we see? So these are the implies and implies conditions. See how I have simplified maximum among other things to just m. Because if m is among this, then this will always hold true. If m is outside, then this must hold true. So just replacing this condition to this is enough. Now we need not care about uh, m being among this or not. If I fix z, then we want x plus y to be greater than z and x plus y to be less than x plus y to be greater than z and x plus y to be and x plus y to be, let's say when they are equal, we also consider them like indices order. Okay, and x plus y should be greater than z comma m minus z, so whatever is max. So this is what we want, right? I don't think this seems too difficult from now. Chaitanya Nandi Nanadhikar, is it fine so far? Do you have Ari? I've seen Ari long back. Which rating today? This one, is it about the line 24? See, Max among others, I'm just sending the Z on to that side, bro. So x plus y plus z greater than max among other can be written as x plus y plus z greater than m, the total maximum. Because if capital M is not among x plus y plus z, then yeah, so I'm just simplifying it. So now what it happened? These two conditions are necessary and sufficient. We need not simplify to, but then it's a simple simplification because when maximum is among these things, then it's always true. Then it's always true. If maximum is outside, then this should happen. If maximum is outside among this, other maximum is true. So instead of true, so m plus y plus z greater than m is true when max is among x plus y plus z is greater than other things is true. So I'm just replacing true with true. Okay, I'm just replacing true with true and covering the other cases. That's how it looks common to both the cases. Okay, that's how we can use logic. I can split these things into two cases, or I can use logic and then I can just write them into mathematical equations like okay, just these things. So now what all I have to do? X plus y greater than or equals to max of z comma m minus z is what I have to see now. Okay, so once you are at z, you want among all the previous pairs, what do you want? Frequencies of these things you want, right? Number of pairs greater than this value is what you want. So let's say you're at z, you have already processed all the previous pairs. Okay, so this is easy to maintain. Let's say when you are a jet, you have already processed all the previous pairs, and then you have a array of. If you maintain uh, frequency of x plus y array for all pairs, we need suffix sum of this shit. I think, right? So let's say for all pairs, all the previous pairs, you are just doing you're trying to maintain this thing, then what you want? Suffix sum of these things, right? You just want suffix sum of those things. Is that clear till here? It's already a sorted array. No, now we want fixing after fixing z, we want number of x comma y pairs such that the sum adds up to greater than m minus z or z, right? So we just want number of pairs whose sum greater than or equals to this value. That's what we want. Number of pairs whose sum greater than or equals to this value. Number of pairs whose sum greater than or equals to this value. So let's say we have that thing g of x plus y equals to number of pairs greater than or equals to x plus y with some. So we are trying to maintain this data structure, okay? Now we are at z. We have the data structure for all these things. When we are at z, what should we do? When we are at z, we will add new pairs to that z comma this z comma that z comma all those things we will add those new pairs, right? When you add those new pairs, I'm just trying to see how we can maintain them well. Okay, we have to solve the problem in n square, right? I mean, I can use Fenwick tree, but I don't want to use Fenwick tree on an easy problem on C, right? There should be an easy way. Suffix sum means I mean, if you maintain this array, then you want suffix sum, right? If you maintain number of pairs with some x plus y, then you want suffix array, right? So let's not even complicate things, okay? Let's fix two things. Let's fix y comma z both because it's an easy problem. If you fix both y comma z, what happens? You have y fixed, you have z fixed. Now you need x greater than max of z comma m minus z minus phi. Just you can just binary search and then find number of such x, right? You can just binary search and find number of such x. Fix x y comma z, and then you are done. I don't know why I was complicating because the problem can be solved in of n square, right? Still, I was complicating. Yeah, two pointers or binary search, both of them works. Two pointers or binary search. See, fix x, fix z, fix y, and then x should be before y. Use binary search to find number of such things. Okay. So we want if you fix x comma y, you need number of let's say capital F equals to this number of x less the x before y and x greater than f. So this is what you want. This you can just binary search, right, to find number of such f. So it can be done in n square log n. I'm trying to see if there is a better way or better approach I can do without doing binary search. We have viewers. Fenwick tree is nothing. We need not use it. It's just some. It can be used to do range operations. That's it. It can be used to do range operations, but it's not needed here. If you see, just a binary search will work. Fix y, fix z, do a binary search. Okay, so let's just do that binary search for now. Okay, we want these things, right? So let me just do that binary search. Right. Now we want, this is what we want now. Simple. Let's try to do binary search for that. Int left equals to, let's assume right equals to I. Let's assume because they are in increasing order, this is greater than f. This is greater than f. This is less than f because both are out of the boundaries, right? I hope you guys know how to do binary search. Even if you don't know, I will explain it. So we have few things in the beginning which may fail, and then few things at the end which may pass, right? Few things in the beginning which may fail, few things in the end which may pass. So, and we have too many things. What we do is we try to find the middle thing, and if it falls here, we can move that to here, and then we will again check the middle thing. We can make two things, one in always failing, one in always passing, and then look at the middle. If the middle falls in the pass, move this pass to here. So you're trying to move closer to the junction quicker. Because you are hopping, you will quick very come to the junction of good and bad. So these things are bad. Let's say this is good at I. So now if a of mid greater than f, that is good, right equals to mid, else left equals to mid. So after binary search, we know from here to I, those are good things, right? So answer plus equals to I minus right. If there are nothing, right will be I, and then that would be 0. Why the fuck is it taking a lot of time? Do you have viewers? Is it boring? Who all are there? Based on that, I will decide what problem I should solve. Who all are there? Can you people say W in the chat or something like that? So that has passed. So this is not that difficult, I guess, right? It's me, rhythm, W. So this is not that difficult, right? But then But then we don't like this complexity. N square log n, is that really needed? If you look at the fact that if y increases, f will only decrease. For a given z, if y increases, f will only decrease. Okay, right? Because if y increases, this is fixed value. Given z, x will only decrease. Means for some y, if you have few failing, few passing, as y increases, what happens? Some failing may pass. Some failing may pass. Okay. As y increases, some failing may pass. So we can move that pointer towards this side. So we have some failing, some passing. Okay. I'll try to write it here. We have some failing, we have some failing, some passing for a given y, comma z, right? For all these things, they are greater than f, all these things less than or equals to f. So as y increases, f decreases, means we get more green things. So what can we do? We can do one by one check if they are increasing or not. We should also verify this thing. If all of them is red, we have to verify if this is red or not. Okay. So let's maintain this red last pointer and then move it to this side, this side, this side as our f keeps reducing. So now what will I do? I will first fix I'll first fix z, and then we are maintaining a pointer, bad pointer. Let's keep it 0. Okay. Let's keep it -1. So if bad pointer is still here, if bad pointer is still here, we will also verify when y is here. We will also verify this thing to see if bad will become full or not, because we have to extend the array also, right? We have to extend the array also. So let's say initial bad pointer is this, and then when you are at here, this is the bad pointer, right? So what's the answer? Answer plus equals to I-1 minus bad pointer, because from here good things start. I-1 is supposed to be the last good thing, right? And then this is the bad pointer. So if I subtract those two things, I will get the good things. Okay. And now, and now, let's make it I equals to 0. So now we have to make if bad pointer equals to I-1. So means if everything is bad, we have to check if this is bad or not. And so let's also have our f equals to f equals to I hope people are there because this is not that difficult. Minus a of 0, let's say, initial value of f. Now what will I do? So everything back a of back pointer, and so just make it 1. And a of I is greater than, so our new f, what is our new f? Minus a of I is our new f, right? This is our new f, right? I plus 1 will be less than n because I less than j less than n. This is our new f, right? So if a of I greater than n, then back pointer plus plus. Back pointer will be I. So what is this code say? If everything is bad and then you're adding a new element, you're trying to see with the new f, you're trying to see if this one becomes bad or not. Okay. If that one is good, that means you have this as green. Now you will try to move as much as possible onto this side. Also some of this might have become green. So we can also first move while bad pointer greater than or equals to 0 and a of bad pointer greater than f, bad pointer minus minus, because now f has reduced more, so we can have new good things. Okay, but then if we had none of the new good things, then we have to see if this also is became bad or not, if this also is bad or not. So this would work. Let's check that. And this is O of n square, not O of n square log n. Okay. See, guys, how was that? Uh-huh. So just by the fact that y is increasing, you can just do linear. This is linear because back pointer, is that linear? Yeah, if it has been n cube, it would have been wrong, right? Because back pointer can only move this side. Yeah, it can only move this side. Whenever it moves this side, it will only move once. Once it move this side, it will not come back. So once it goes behind, it won't come back. It's sometimes moving this side too, but then once it goes here, it won't come back. If it is coming back again, then it's a problem because we are doing plus plus, we are doing minus minus, right? If it's coming back again, then it's a problem. But even if it is coming, it won't come more than plus plus is just one move. It's yeah. So now we have to solve another problem. Okay. Now that we have solved an easy problem, I won't go easy on my viewers, right? So we will read one more problem in whatever the difficulty of f that I have chosen before. Okay. Stay, people. Let's try one more difficult problem and then close the stream. Okay. Just try. I won't get stuck like yesterday. Okay. I promise. I won't get stuck like yesterday. Let's try another problem. See, reading the problem is important. It really improves your skill. It's not about solving questions too. Is it fine now? No, I will read a random problem if that's fine. See, we will try to read quicker, bro. Read quicker. See, we will try the problem more time. So it's fine, I think. Let's keep just 29. Yesterday I have chosen F in that same way. I don't want to see the rating tags though. I don't want to see these rating tags because they are bad in some way. So, what should we try? Try this one. We have modulo 3. I tried submitting some wrong TLD because this would not DSU roll with rollbacks wouldn't work. It will only work if it is amortized. Otherwise, it wouldn't work. So that's a wrong submission right there. This doesn't look that good to me. What is this? Let's read that. Okay. See, guys, let's try to read problems. Okay, read some problems. Okay, we have to read some problems. Reading problems will do more good to you. Really, you guys will never do that, right? At least do with me. Okay, read. At least try to do with me. So we are trying to read this problem now. Okay. Hey, people, are you people here? This is going to be an interesting and good stream, really, because I am parallelly trying to make sure that this is good. Thanks. This is going to be a good stream. So let's read this problem. Reading is important. I will be quick. I won't waste time like yesterday. I'll keep the link. No, bro, I won't try that problem. I have seen the solution already. I won't. I have asked with someone else for the solution. I have tried the contest, tried that question in contest, so I can try it again. So let's read this problem, guys. Let's read this problem. Okay. Let's try to see how difficult it can be. Let's try to comment on the problem because we have to comment on the problem. We have to judge the problem. Okay. Uh, to be better at physics, can you guys see the question? Ayn wants, okay, let's read this too. If I was also hit by an apple falling from an apple tree, could I become as good as physics at Newton? Definitely not. Newton is fucking genius, right? To be better at physics, Ayn wants to build an apple tree so that she can get hit by apples on it. Okay? Apple tree has n nodes and is rooted at node 1. Okay? She defines the weight of an apple tree as for I equals to 1 to n, for j equals to I plus 1 to n, for all pairs, depth of LCA of that. Okay, here depth of x is defined as the number of edges on unique shortest path from 1 to x. That's what depth in general is, right? LCA is just least common ancestor, okay? For some old books and reads, she knows that Newton's apple tree's weight is around k, but the exact value of it is lost. I do read chat. So one thing is very clear in any question I read. I know there won't be any topics because even here what topics can be there. So let me not distract. Let's try to see the problem. For some old books and reads, she knows that Newton's apple's tree weight is around k, but the exact value of it is lost. So what does this mean? She knows the Newton's apples tree. We have some Newton's apples tree. Its value is around k, but exact value is lost. As Anne's friend, you want to build an apple tree with n nodes for her, and the absolute difference between your tree's weight and k should be at most 1. Unfortunately, this is not always possible. In this case, please report it. So, topics will not be there at all. Let's try to see that. So depth of a tree, sorry, weight of a tree is defined, and uh, depth of all pairs, LCMs of all pairs. See, LCA is, I hope you guys know, in a tree, in a tree, in a tree. See, don't think this is not for you people, okay? Because this is for newbies. LCA of these two is least common ancestor. All of these are ancestors. All of these are ancestors. So this is the least common ancestor, right? With the highest depth. So depth of LCA of all pairs. And we are given K. And then we have to build a tree with weight. K or K minus 1 or K plus 1. That's what this says. If not possible, return no. Else return S and some tree. So this is about trying to find what all weights are possible or not. Maybe we have to experiment what all weights we can get using some specific structures of tree. We can experiment that, or we can try to see if we can simplify the depth formula. Even this we can try, but this is because here there is an experimentation. I will not try this question in this stream, okay? I will not try this question in this stream. Let's move to some other question, okay? This I was scared long last time. Towering arrays, we have just tried fallen towers. Should we try towering arrays now? Let's try towering arrays, okay? I think I've read this problem sometime. It's scary. But then these things are also not being that good, right? Should I reduce the difficulty? Are we scared? So, guys, you're not understanding. Reading problems helps you people. It's not just solving problems. Reading problem really helps you people. Reading this problem will help us. It's like we have to experiment some structures. So let's read another problem now. Towering arrays. Let's read this problem too. Okay. I understand that. I understand that. I'm being weird, but let's read this problem too. Okay. Let's read this problem too. Because if with me, you people are reading these problems, you with alone you can read 2200s. With alone you can try 1700s. With alone you can try 1900s, right? So with me, try something that's difficult for me too. Because then you can then if I try 1800, you may say, oh, he's trying easy problems. Maybe I cannot try that, right? That's why I'm trying to try these things. You also should try these things. Try with me because, okay, get what you take. Sorry, take what you get. We're reading this problem now. Read with me. Another problem. Read and judge the problem. This will increase your rating much more than whatever topics you learn. Trust me. This is my way of solving, my way of learning. Read the problem now. We're reading this problem now. An array B of length m is called p-towering if there exists an index I such that for every index j 1 less than or equals to j less than or equals to m, the following condition holds: bj greater than or equals to p minus I minus j. We have some weird formula. Okay, I haven't read this problem, so I can try it well. Given an array of length n, you can remove at most k elements from it. Determine the maximum value of p for which the remaining element can be made p-towering. So this has steps. First, we have to think on what's a p-towering, and then we have to actually answer the problem for being able to remove any k elements. What's the maximum p-towering that you can attain? See, it has steps. Means it is solvable. Not solvable. It is at least you can try to do something. It's not like one big blockage, right? You can try to work on this thing first, and then you can try to work on this thing next. You can try to work on what it means to be a p-towering, and then you can try to work. You have to solve this too. So this we can try to work on the problem because it's not blocking us, right? Even the previous one is not blocking, but it has experimentation. So I don't wanna try random things on stream. It's difficult. So let's read this problem now. So have you people read the problem? I will try to follow up with one person. Okay. Uh, whom should I try to follow up with? Chaitanya Nanadikar is trying to show some interest. So Chaitanya Nanadikar, have you read the problem? Or also Anirudh Saraf. Also Anirudh Saraf, have you read the problem? Yeah, you have read the problem, right? So it has two steps. First, we can try to think of this, and then we can try to come. See the problem. We have to prove the problem. Once we solve, we will also prove that any k things you remove, this is the maximum p-towering you can attain. So somehow we have to go there. So this must be simplified a bit. So let's try to see what it is. An array A B of size m is p-towering if bj greater than or equals to p minus of I minus j for some I. It's for some I. Bj greater than or equals to p minus modulus of I minus j. It seems. So what is this thing? What is p minus I minus j? Let's draw here. M 0. This value is less than p, right? So let's say this was I. Suppose this was I. So let's say this is p. At I is fixed. At I it takes p, and it goes like this, and it goes at m it will take p minus, and it goes like this. Right. For this I, we want all the values to be above this shit, it seems. As it looks interesting, it seems we can do nothing, but still we should see what we can do. We should see a bit more try before concluding. But Chaitanya Nainadikar, the problem looks different from what you expect from a high rating problem, right? Was that graph necessary? I just made it because for no reason, just to see. Because now for this P, you can vary this thing. I can vary, right? It could have been this too. And then we have to say, even if elements fall here, we have to say that. Right. And then there is a p. Let's say p is 0. That works for everything. If p is 0, that probably works for everything, right? Or p is 1. P is 1 works for everything. So here we have p1. See, we must solve this problem first, because if k is 0, let's take k as 0, means you must solve the problem of finding what's the maximum p given an array. So let's work on that problem first. Solve the case for k equals to 0. So let's work on. We can try to work on this, right? Yeah, I also don't know much. We have to understand what that formula means so that we solve the problem well. Okay. We have to understand perfectly. And also, I is varying, right? Is there some I? Even this is there. Is there some I? Right. So, if we fix 1j, okay, let's fix 1j. Let's try to rearrange it a little bit for fun. Let's try to see. Let's say I greater than j, bj greater than or equals to p minus I plus j. Right. Or bj minus j greater than or equals to p minus I. Let's say I less than j. Then we have bj greater than or equals to p minus I plus p minus j plus, okay, j minus I, which is p minus j plus I, which is bj plus j greater than or equals to p plus I. I'm just doing this for fun. Okay, we should not get stuck here. Let's just see this for fun. And then I'm trying to just separate for 1j what all p comma I are possible. Okay, for 1j what all p comma I are valid for some particular j, because this should be satisfied for all j's, right? And for some I and some p. See, for some I and some p, this shit should be satisfied for all j, right? So let's look for some j. What are the p comma i's that satisfy? And then we want some minimum p for which there is some p comma I. Okay. Nigga, watch JE videos. I have to make JE videos too, because I can solve physics, I can solve math, and I have a bigger audience there, right? I'm just joking. But JE videos anyone can do. These problems I think only I can do. So if is this clear? So for each j there are some p comma I pairs. So this is just a restructure, right? This is just a restructure of the same problem. We have a fixed p, we have a fixed I, and then we have this formula. I'm just giving j more importance, and then I'm just trying to remove this modulo and try to see what all p comma I is satisfied with. You guys should spread my coding streams and get me 1K subscribers, because I'm close to 1K subscribers. It's not that easy to shout at night 12 o'clock, right? Yeah, I'm just fixing j and see how what all p comma I are satisfied. Okay, so if I fix p, if I fix j, there are some p comma I pairs possible, right? And then what do we want? In the question, we are fixing p, we are fixing I, and then we want all j's to satisfy, which is nothing but for we want some p comma I that is satisfied by all j. In that, we want maximum p. Okay. So let's look at these things. For a particular j, what all I comma uh, so for a particular j, let's look at a particular j. Okay, damn, this line is so straight because it's zoomed up. So minimize things, draw a straight line, fucked up straight line, and then zoom it. It's not straight though. This is fucking straight. There you have a straight line. So let's look at a particular j. Okay, and then we have two values. What are those two values? Comma bj minus j. Let this be p. Let this be I. Okay. Let's try to see what all I comma j p comma I pairs will satisfy these two equations. So for this j, for I greater than j, we have. I mean, this is not needed maybe, but let's just try that. We have. See, the thing is, we at least we are able to try something. It's right or not. Being able to try or getting stuck are two different things, right? Let's try something. Trying something will only improve your skills. So, what is this? P minus I, P plus I, Bj minus A, Bj minus J. So we have P minus I. How would that look? Let's keep I as J. Okay. If we keep I as J, if you keep I as J, you have P less than or equals to Bj in both cases. So we have some Bj here. P less than or equals to Bj. All of these will satisfy. Wait, where did those things go? Where did the colors go? I did something and then the colors are gone. Hey, colors are back. So all these things are satisfied. And from here, what is this line? P minus I. So P is positive, I is negative. Means if P increases, fuck, wait a minute. How does X minus Y line looks? X X minus Y. It will be like this, right? So P minus I fixed will look like this. And then we have P minus I less than or equals to these things, right? So with decreasing P is good. So all this is green. And then we have P plus I greater than or equals to bj plus j. And how would that line look? At I equals to j, it would be here, because at I equals to j, p is bj, right? P is less than or equals to bj, so even that line will be here. And then in this case, p is less than or equals to, oops, this thing. So for some j, this is the value, and these are the green things we have. Okay, do we have viewers? You guys are talking to each other. I have very few viewers, and even if those viewers are not focused on the stream, it will be pretty useless, right? Chaitanya Nanindikar, you're trying, right? Kailash Chaudhary, you're also trying, right? So, for a J, this for each different J, this point is different. Do you see that? For each different J, this point is different. This point is different. It's like for the next J, it will be somewhere here. For this J, it's here. For this j it will be here, for this j it will be here, for j equals to 1 it will be here, j equals to 2 it will be here. So we have these things at many places. At all these places we have those things, like here, but then this bj value will decide where it falls. And then what do we want? We want some point that falls in green region of everything with maximum p value. Okay, do you guys see this? Guys, people are following, right? At least little bit. See, I fixed j. I fixed j, and then I'm drawing graph of p versus I. What all p comma I pairs satisfy. So now we have some idea. Let's look at two different j. How would they follow? Let's just look at two different these structures. How would they appear? So let's look at two things. One is here, let's say. If something else is here, if something else is in this region, this is useless because this restricts better, right? This thing restricts better. So if something is like this, then this is waste. I mean, not waste. This we need not consider. Only this will help. If this is if this thing covering it totally, okay. This thing restricts. We're trying to solve the problem when k is 0, and for any two things, either this covers it entirely or we have those L structures like this and like this, right? That's how we have. So we have for any two things, either one covers the other thing totally or they form something like this, right? So let's look at one thing. Let's look at the lowest thing itself. Let's say this is the lowest thing. Okay, and then the above thing will be entirely covering it, or just comes just one above, right? The one above thing can be, if it is here, it's useless. J equals to 1, let this be j equals to 1. For j equals to 2, if it is here, it's useless. If it is here, it's useless. If it is here, it will be like this. If it is here, it's again useless. Damn! Do you see that? Am I fucking things up, or even if it is here, it's again one of them is useless. I thought the final structure will be something like this, this, and so on. But then the final structure is being okay, okay. The final structure is being this and then this. Or for two element things, it's either this or this. But if you notice, these two can be viewed together like this being the main, and then two things. Okay. I hope I hope some of you are following or getting something, because if you guys have tried with me, I know Russell's paradox little bit. It's like set containing all the sets in themselves or something like that. No, but I won't do that now. Okay. So next CD, we are making progress here, or so, at least some people are hooked up compared to yesterday. This being better. So let's try this. So being useless means if it is here, we are only having one thing. It's being this structure is what I mean by useless. If it is here, we are only having this thing. So if we are seeing two things, these are the only two structures we have. Okay. And now if this is the structure, we know the new structure can only be again these two things. Let's look at this thing. If a new thing comes on here, I equals to 3. If you look at I equals to 3 on here, let's say I equals to 3 is this one. Let's say I equals to 3 we have here. If you look at I equals to 3, if it is here, it's useless. We have the same structure. If it is here, we have the same structure. It's all useless. If it is here, then we have this coming up. If it is here, then this structure is possible. Right? But if it is instead of here, if it was here, I fucked this up a bit. It was here, right? Yeah. Instead of that, if it was here, then we have this structure. If it was here, we again have unique structure, right? So if you look at this sheet, if you look at this sheet, it's being, it can take this kind of structure, or it can take uh, this structure, or it can take this and then this jump and then this. So if it's looking like some steps, right? If you see crossword, if you turn this side and then if you see crossword, it's like either this or two steps above and then this, or directly from here to this. These are the only kind of things that's being possible, right? Like from here, go one, two, three steps and then done, or go one step like this, go two steps like this and then done. Go one step like this, go one step like this, go one step like this, go one step like this and then done. So these are the, structures that are being possible, right? For, n element. Sorry, for 3, I equals to 1, 2, 3. And we can see most of the times we want maximum j, right? We want maximum p. So for all these structures, this is 1 above, right? So this is 1 above. This is I equals to 1. This is I equals to 1. This is I equals to 1. So for I equals to 1, we have this thing here. That seems the best one, right? Always I equals to 1 seems the maximum p, right? Because you're going 1 and then you're coming this. Or or you could have gone like this, one step like this, one step like this, one more step like this, and then maybe like this too, and then maybe also this could have been it. In this case, maybe this is not the best. Maybe we have some other best here, okay? If there are any new people, like the video, okay? How to sleep. So let's try, let's not get disappointed, let's not do anything. So it's like from start from you will start from here. Let's say this is j equals to 1. We'll start from here and the structure is some steps, and then it's gone. Maybe the steps are just like this and like this. Maybe the steps are just like this. But from here, at each step, you take a step. And then that's the structure. Like we have n steps, n possible steps. Okay. We have n possible steps that goes like this, like this, like this, and this. Okay. So if you notice, I think if that's just the structure, at any y value, you will probably get the least x somewhere around here, right? It's like intersection of two adjacent y values. Like if you take two adjacent y values, see these kind of things, this kind of pointed corners occur only at j values, right? Pointed corners occurs only at j. And then if you see adjacent pointed corners, they can be like this or they will be like this, right? Adjacent pointed corners will only be like this. So all these corners, these points are only happening for adjacent things, right? These things are only happening for adjacent things. For k greater than 0, let's think of that. But at least we have to solve k equals to 0 case in O of n. That's our first goal, okay? and then we can think further. See, max p is nothing but whatever the green point with max p. That's it. Whatever the green point with max p. Okay. So if it was like this, then at n, this is I, this is p. Then this would have been the max p answer. Okay. The final, if the final structure would have been like this would have been that. If the final structure have been this, maybe then this would have been the answer. But can we claim that answer is always now? Answer is probably one of these two things. Okay, this value would be the answer, this p. I think in often we can solve this problem. We can surely solve this problem in often, right? Because we can just draw all these things and then we can just draw all these things and then we can just solve the problem, right? Because we have n things, right? In often we can surely solve the problem by going over all vertical values for all possible i's. You will just find the minimum p. For all possible I, you just will just find the minimum p, and then you're done. Wait, we can even see these things as this green area or this green area, this or this. No, but then we have to take this or this and everything, right? So the final structure is not this. Final structure can be zigzag because this or that's what we have worked on so far. But yeah, again, this that logic will not help. I was trying to see if it gets simplified, but then we know the structure can be arbitrary like this. It can come till here and then it can go more, and then it can come like this, and then it can go. So this intersection is among this and this. If you see, now this would be the max p. So see guys, for in often we can solve this now probably because we can somehow make this thing and then we can solve this in often. Okay. See, this line, this constraint and this constraint are just two lines, and then all this side will satisfy, all this side will satisfy, because these points are I comma p pairs. So the graph thing is understood, right? The graph thing is not much. I am trying, bro. Don't you see that I'm trying yesterday for 3 hours, and don't you see that I'm trying today for 2 hours? I'm trying when you're not. Uh, is that fine, Kailash and Ash Mohta? See, we are just trying to see how the structure is, right? We don't know. We're trying to see how the structure is. Okay. So now what do? We remove few things, because now we can solve the problem in O of n when k equals to 0. Probably we can somehow try to find the least point of k in O of n, right? A or B and C or D. Is nothing but A or B and C. So see, we have two lines. We have n two n lines, n these lines and n these lines, right? We have two n lines. So these lines, let's try to look at them in a proper way. So let's this be I equals to 1, okay? So we have these lines like this, like this, like this, like this. Let's try to look at this coordinate system kind of thing. And then we have some lines like this, like this, like this, like this. So among these things, let's look at this. Let's look at like this, okay? Let's look at this coordinate system. Like, let's look at all these things, okay? Let's look at these things. So now, in these things, we have endpoints, okay? We have endpoints here. And if you look at cross, we can have some points like this. So when we are moving like this, it's all about trying to see what all the points that will fall on here. And then from here, we only go above like this. So it's like, so we have some points here. In this cross thing, it's like in this cross thing, so in this cross thing, we have some points and then it goes like this. So it's nothing but a step. So if we turn that like this, it's nothing but n steps, which I already concluded. It's like nothing but n steps, n steps. Steps can go like this, or the n steps can go like. And in all of these possible n steps, what do we want? This maximum value of this thing. So it's like we want, if in this, if you look at x minus 5 values, y minus x values, like these things, if you look at these lines here, we want this line, this length to maximum. Like among this, among this good region, if you draw these lines, then this should be maximized. We want somehow that thing, okay? So in O of n, I can find. I will go over this, and then we can see only these intersections matter. Only these intersections matter, right? Because probably they will take the maximum y value. So I will find this point, 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 and then for all these points, I can find the maximum. See, if I find all these points, like these points too, because we only get these points from here, right? And then I will find also these points, and after finding all those points, maximum p among them is the answer. So in O of n, we can do this clearly. Oops. Okay. In O of n, we can do this clearly. Fuck, only three people. Good night, guys. Probably. Who all is there? Zero people. Damn. Hey. Hello. So let's try to think. Let's try to think. Uh, See, we know how to do this for often. Okay, because we have these endpoints, and then for each of these cross lines, I can find the maximum, the other point, and once we have all the best points, then then we can try to take whatever the maximum is. Prefix max. We will do the prefix max like from this side. Okay. So now we have to remove things. Let's try to see, because we can solve this in O of n. Now try to see what happens. Now let's work on changes if you remove some elements. Then we remove k best things. This seems very simple, right? I'm just doing one. I did all of that on graph, and then I'm coming here, and then I'm just telling, let's fix P, because bind research will work on P. I don't know why I have done all of that. Maybe I expected more of the problem. Yeah, but let's fix P, and then try to see often if we can do this. Often, let's try to find if we can find k things. Okay, so we have to do often, right? We brute force I, let's say. Okay, we brute force I. So means brute forcing I is nothing but we're trying to go over for some p For some P, this is P, right? Let me use orange for P. For some P, I'm trying to go over all those I's and then try to see if at least one of them satisfies, right? Right. So if we can get quickly for each I after fixing P, how many don't satisfy? So once you remove something, that J changes, right? It's not is what I'm thinking. Okay, problem. So guys, we have one big question in front of us. Is there Kailash or is there like someone else? We have one big question in front of us, which is to remove something. How does the graph changes? That's one big question. Because if I can make an assumption that if I can make an assumption that let's say this is the thing we have three things. If I can make an assumption that if I remove this thing, then this won't be the answer anymore. What happens? The thing falls below. I think these two are in the same level, right? The thing will fall below, and then this would be the answer. That makes it more complex. When you remove something, it will fall down. But still, the problem is solvable. I mean, otherwise, it will be too. We have to think a bit. Let's see. You people understand the complexity, right? Why it have happened? Because the thing falls down. But still, if you find some observation, maybe the problem is solvable. Do you guys get? If you find some observation, the problem may be solved. So, can you guys handle reading one more problem? Like in 15 minutes. Like the people that have existed so far, can they take that? Mosh Mahota. Sorry, Yash Mahota. Are you there? I'll read one more higher rated problem and then I'll stop. Okay. Just read. Maybe summing. Counting is not fun. Stop gaming, Zord of Median. If I go down and I was solving more and more problems, let's see here, like if I'm solving, like at some point I would be solving more problems, right? See, sorry. At some point I used to solve more problems. Like, see, almost more problems. At least I have to get to that level, and I also focus on speed now. See how many problems I have tried, like in this region itself. See these things. See these things. I might have read every problem and have gotten these problems. Do you see how much I try? Long back, not now. Solving them all on my own. If you look at some solution in 2023, so just this. Uh, with this one, I'm not even writing solutions at this point. All are small solutions, right? This was a good problem, I remember it. So, guys, let's read one more problem, okay? Let's read one. That's what we are trying to do in these streams, okay? What's the one more problem? In the first page, let's try one more problem, okay? I have tried haystacks already. Let's not see the ratings. Uh, let's not see the ratings because if you see the ratings, we'll get scared. Maybe this. Oh no, that seems weird. Two subarrays or maybe cactus connectivity. No. Let's go for some problem, any problem. Should I try something like that has harder version? Nah. This is that hacking numbers. Damn, is it 26? Is it that difficult? Okay, this I haven't seen. This I haven't seen. But then C3 is C1 and C2 are also needed, right? Cycling. Maybe I'll try easier version, the harder version. I'll go for a nicer problem. Homework. I mean, actually, all problems are nice, but then at this time, let's try this. Okay, really. 3. This also I'll open, but then it has many things. Okay, let me read this. Interactive problem. Welcome, duelists. In this interactive, there is an integer x. You must make it equal to a given integer n in the input. By harnessing power of math, make monsters. You can do one of the following. F of n be the minimum number of operations such that there is a sequence of f of n commands that transforms x into n for all x. You people also try to read the problem, maybe. Fuck. So what does that mean? What is it? Sum of all individual digits, it seems. Okay. Even we have that here. Yeah, we have add mul division. Add y will do x plus y. Mul will do x into y. So f of n, so f of n is less than or equals to 4. Fuck, really? So Ari, this means let's try to solve this problem first. Whatever the n is, we can make whatever the x is, we can make it to n using four operations, right? Seems easy somehow. So we should not be doing zeros, because we'll probably not be doing zeros, okay? We will try only once probably, because we should not cross the values, okay? We can add anything but we should not cross the values, okay? Otherwise we will lose our operation, right? So four commands, maybe we will make any x to 1 and then we will multiply with n, right? Right. Seems too easy. We have digit 2, right? Let's say what's the maximum value of sum of digits? 9999999, right? 8 times, which is 81. What's the max value? Maximum 18, right? If we digit that again, we will have a single digit probably. But still, how can we make it n in one more operation? Let's try. Let's try a little bit. I think digit must be. This seems easy. Four operations. Let's just try to think. Okay, digit, digit. See, we need something deterministic. At some point, we should know what's the value of If n equals to 1, how do you manage? If you can do this in 3, you can do anything in 4. Can we make it 1? Digit of this, if we apply digit once, apply digit twice, this should be easy, right? We should try random things here, not too random, but let's try to apply some logic to get it quick. We should deterministically make. How can we answer this question in 4 steps? Maybe we will also use the information of 1 and 0, maybe. Okay? Let's apply 1 s of x. Okay? Let's just apply 1 s of x. So now the value is small. Can we try something? First thing, let's the first thing be digit of this. So now the value will be less than or equals to 81. So now we should make it 1, right? Binary search, right? 3 operations. If you are getting 0, means it became negative. I mean less than or equals to 0, and we can find like binary search. What is C1? 7 operations. So that can be done probably with binary search. So on 81, we can do some binary search, I guess. Maybe apply twice, and then we have 5 more operations, right? In that 5 more operations, you can find using 4 operations. You can find Not even binary search. Let's try this. 2357 or the primes, right? If it's divisible by 2, if it's divisible by 3, if it's divisible by 5, if it's divisible by 7, we can know these things using 4 operations. But then, if this happens, let's say, we'll check this. If 2 happens, we will check if it is 4 or 8. Or else, if 3 happen, we'll check with 6 and 9. If 5 and 7 happens, we don't do anything. So this comes under 6 operations, I think. So 7 operations. 2 operations, it became a single digit. We have we are checking if it is divisible with 2. If it is, then so 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5. So this comes under 7 operations. I'll check with 2 divisible or not. If not, I'll check with 3 divisible or not. If it is divisible with 3, I will check with 6 divisible or not. Right? If, if it is 3, I can check if it is divisible with 6 or not. Okay, if it is divisible with 2 and 3, you can get both of these things to qualify 6. If it is divisible by 2, we can check for 3, 4, and 8. For this, let's just make 6 here. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And if it is divisible by 3, 1, 2, 9. So this 7. What the fuck? What the fuck? That's a nice thing, Zia. Thanks. That makes us deterministic. So multiply by 9 and then take digit and digit. So that's the solution for C2. What binary search works for C2? So maybe then I'm just copying your solution, bro. I can only solve easy problems, probably. It's not going to solve C3, Niga. It solves C1. C1 is binary search, but let's see the solution too. Zaid, you have to solve C2. Just one query, reduce one query. So C2, how to solve C2? Guys, tell me how to solve C2. Okay, add whatever you want. See, guys, here I will try to flex my proving skills again. Okay. I don't know why I was not talking. Okay. So, what I will tell you people is, as per logic, if you don't apply digit, so now I'll try to use some logic because I can. Uh, so where is C3? If you don't apply more digits, okay, we have x in between. So let's say you don't apply digits at all, then x can be in between and 1e9, okay, but you can at max do, let's say, three operations, okay. Then whatever happened, what's the information you received? You receive 3 bits, just 3 bits. You cannot map those 3 bits into two greater than 8 elements. Do you see that? How is this logic to prove things? Hey, is that fine? We must apply digits because if you don't apply digit, we have 3 bits of information, 0 1 0 1 0 1. You cannot map that to greater than 8 elements, right? So if you don't apply any digit, it's unsolvable, right? Because after three operations, in three operations, you only have three bits of information. You cannot map that through all x because all of these are seeming deterministic, right? By deterministic, what I mean is you cannot take floor or seal. You have to know something. See, whatever you will change the value perfectly, or it won't change at all. So you cannot know more information probably than this. If there is some floor division, maybe then you can try, but still, we must apply digits, okay? So if you apply one digit, now values are less than 81. See, I think Z, C2 and C3 would not be too much difficult. C2 and C3 wouldn't be much difficult. It's just finding some cases of n where you can 2 is impossible maybe because can you solve in two operations? So if you apply one digit, now values are less than or equals to 81. Now can you solve this in one operation? Now can you solve this in two operation? These are the things we have. This is probably no because we have 81 different things. Let's assume that digit is being applied front, okay? Otherwise, it's even worse, right? Otherwise, it's even worse. So, so what do we have here? One, two, three operations. If n equals to 9, we can do in three operations. There is at least someone who has just tried this on C3. But then it would be too easy, right? See, we haven't used division yet. Maybe we do division here with 9. Hey, we have 3 operations. We have 2 operations. What are these things? Okay, these are just shitty. These are just shitty. What does it say? So for 100 comma 9, they took three operations. But for 1, 2, 3, 4, let's check for 1, 2, 3, 4. Okay. N is 5. Let's try to understand this once. Adding minus 10 gave you 0. This means x could have been lesser also, right? What the fuck is this? How do we know what is x? Maybe this is just some bullshit, okay? Uh, but let's say this takes 4 operations. If n equals to 100, let's say 4 operations is the way. If n equals to 5, do we have 3 operations? We have to think. So 11 works. Right. So what do we do? How does 11 works? Reminder with 11 doesn't change after taking sum of digits. Let's verify 11. Fuck, 11 itself changing. Okay, alternate sum. Sorry, 11 is wrong. So this gives a0. I wrote it reverse minus a1 plus a2 up to so on. If this is divisible by 11, then the number is divisible. So a0 plus a1 plus a2, we don't have much of it. What about 99 plus 1, such things? Didn't get you, bro. I can't think. You only should help. Largest possible multiple of 11 means? I think there is some multiplication. Plus negative value. So let's think, bro. It's a nice problem. Now let's just think logically. We are not sleeping until we solve this shit. 11. There is some multiplication that makes digits into. There is some multiplication. So if these two are the one two things, using one more bit, we cannot separate these many numbers, right? Because if these two are the one two things, we have these many different possibilities. Using just one more bit, you cannot get more information than two, right? You cannot split these things. So this is definitely, there's no way. Multiply by 9 and then this, there is no way. Is there some other multiplication? I fucked up multiply by 11 because It's not even getting a smile on my face. Maybe I need water. I'll get some water. Let's stop this. So see, if we apply first 9 and then digit, then we will be left with these things. We cannot do them in one more operation, right? So multiplying with 9 and then digit doesn't seem reasonable. So probably first is digit. After first is digit, what can we do? See, is there a number? Is there a number added to all? Bro, last operation is digit. This is for sure, Zaid. If last operation is not digit, that says after second itself we should become deterministic, right? That's not possible, right? So last one is digit. So now we have two more before this. So I think most reasonable is digit, sum, mul, or add that makes them different values but with same sum. See, because other operations will only give us 0 or 1. With that we cannot get more information, right? But this digit can combine multiple things into one thing. So if we can make these two digit numbers into something like this that will give us same sum, we are done, right? Is there a way to convert two digit things into same sum? Is there some number when multiplied with any digit gives same sum? There is. What's 19 ones? 19. What's 19 twos? No, there isn't maybe. Let's see. 38. I think there is some number. Is it 9? Right, we have this thing, right? So if I multiply with 909, what happens? 9009. Any two digit number. What happens? It becomes 909. It becomes, we got somewhere, I guess, finally. 1818 or 1827, or all these things add up to, if you do sum of digits to these things, you will get, you will get what? 18, right? When if I means shift them like this, and then we have five zeros minus this number. So 1 if I minus 1 is, shift them, you have five zeros, But see this one, bro. Here we are able to get 19. Most of the time we are able to get 19. 18. 909 itself. But then if it was 10, we would have gotten 1800. Sorry. Wait. If you multiply with 909, what happens? Wait. 909 times 2. We have this thing. We can separate them. Stop, guys. Let's stop. Guys, let's stop. We should really stop, I think. Yeah, bro, there is some pattern. Yeah, we should do that. Bro, we should not wake up like this, bro. But we are taking hours. He was in the contest, right? So let's leave it. It's being useless.